Welcome back to JVM Internals Crashcasts. I'm your host, Sheila, and today we're diving deeper into the JVM memory model. For our new listeners, JVM stands for Java Virtual Machine, the runtime environment for Java programs. Specifically, we'll be exploring the various memory areas within the JVM in detail. Joining me as always is our JVM expert, Victor. Hey Victor, are you ready to navigate through the JVM's memory landscape?
Absolutely, Sheila. I'm excited to break down these memory areas and help our listeners understand how they work together to make the JVM tick.
Great. Before we dive in, let's start with a quick quiz for our listeners. Here's the question. Which JVM memory area is responsible for storing all class-level data, including static variables? Think about it, and we'll reveal the answer at the end of the episode.
That's an excellent question, Sheila. It really gets to the heart of how the JVM organizes different types of data. I'm curious to see how many of our listeners can guess the correct answer.
Now, Victor, before we get into the nitty-gritty of each memory area, could you give us a high-level overview of why the JVM needs different memory areas in the first place?
Certainly. The JVM divides its memory into different areas to efficiently manage various types of data and operations. Think of it like a well-organized office where different departments handle specific tasks. In the JVM, we have areas for storing objects, managing method calls, keeping track of thread execution, and more. This separation allows for better performance, easier garbage collection, and improved memory management overall.
That makes sense. It's like having different rooms in a house for different purposes. So let's start breaking down these areas. I understand there are 5 main memory areas in the JVM. Could you list them for us?
You're absolutely right, Sheila. The 5 main memory areas in the JVM are 1. The heap, 2. The method area, also known as metaspace in newer Java versions, 3. The Java stack, 4. The program counter, PC register, 5. The native method stack. Each of these areas has a specific purpose and characteristics.
Let's start with the heap. I've heard it's where all the objects live. Is that correct?
That's right, Sheila. The heap is the runtime data area where all class instances and arrays are allocated. It's the largest memory area in the JVM and is shared among all Java virtual machine threads. Think of it as a big warehouse where all the objects your program creates are stored.
Interesting. So if it's shared among all threads, how does the JVM manage concurrent access and prevent conflicts?
Great question. The JVM uses various synchronization mechanisms to ensure thread-safe access to objects in the heap. This includes features like locks, volatile variables, and the Java memory models happens before relationship. However, it's important to note that proper synchronization is often the responsibility of the programmer when writing multi-threaded code.
I see. Now, what about the method area? Is that where our actual Java code is stored?
Close, but not quite. The method area, also known as metaspace in Java 8, and later, stores per-class structures such as the runtime constant pool, field and method data, and the code for methods and constructors. It's separate from the heap and is used by the JVM to store class-level information rather than instance-level data.
I think I understand. So, the method area is more about the structure and metadata of our classes, while the heap is where the actual objects created from those classes live.
Exactly. You've got it, Sheila. Now, let's move on to the Java stack. This is a really interesting area because it's closely tied to how our programs actually execute.
Oh, I've heard about the stack before. It's related to method calls, right?
That's correct. The Java stack is created for each thread when it's launched. It stores local variables, partial results, and call stack information. Every time a method is invoked, a new frame is created on the stack for that method call. When the method completes, its frame is deleted from the stack.
That's fascinating. It's like each thread has its own to-do list, keeping track of what methods it's currently executing and what it needs to do next.
That's a great analogy, Sheila. And just like a to-do list, the stack operates in a last-in, first-out, LIFO manner. The most recently added item is the first one to be removed,
Now, what about the program counter register? It sounds quite technical.
The PC register is actually quite simple in concept. Each thread has its own PC register, which contains the address of the Java virtual machine instruction currently being executed. If the method is native, written in a language other than Java, the PC register is undefined.
So it's like a bookmark for each thread, keeping track of where it is in the code.
Exactly. That's a perfect way to think about it.
And finally, we have the native method stack. I'm guessing this has something to do with native methods.
You're on the right track, Sheila. The native method stack is similar to the Java stack, but it's used for native methods written in languages other than Java, like C or C++. It allows Java to call methods written in other languages through the Java Native Interface, JNI.
Wow, that's a lot to take in. Can you give us an example of how these memory areas might interact in a typical Java program?
Certainly. Let's say you're creating a new object in your Java program. The class definition for that object is stored in the method area. When you use the new keyword, space for the object is allocated on the heap. If this happens inside a method, the reference to that object is stored as a local variable on the stack for that thread. The PC register keeps track of which instruction is being executed, and if your program calls a native method, the native method stack comes into play.
That really helps tie it all together, thank you. Now I'm curious about common pitfalls or misunderstandings developers might have about these memory areas.
One common issue is not understanding the difference between the stack and the heap, which can lead to memory leaks or inefficient memory usage. Another is forgetting that the heap is shared among all threads, which can cause concurrency issues if not properly managed. It's also important to remember that while the JVM handles a lot of memory management for us, understanding these areas can help us write more efficient and bug-free code.
Those are great points, Victor. Before we wrap up, let's reveal the answer to our quiz question. Which JVM memory area is responsible for storing all class-level data, including static variables?
The answer is the method area. It stores all class-level data, including static variables, as well as the structure of the classes themselves.
Thank you, Victor. To summarize, we've explored the 5 main memory areas of the JVM: the heap, the method area, the Java stack, the PC register, and the native method stack. Each plays a crucial role in how Java programs run, from storing objects to managing method calls and thread execution.
Exactly, Sheila. Understanding these areas can greatly improve a developer's ability to write efficient Java code and debug memory-related issues.
In our next episode, we'll be diving into object structure and memory layout. Until then, keep exploring the fascinating world of JVM internals. If you enjoyed this episode, please subscribe to JVM Internals Crashcasts and leave us a rating. Your support helps us continue creating valuable content for Java enthusiasts everywhere. Thanks for listening.